this is Susie Newhan, and this is the one about solving linear simultaneous equations. So here's an equation, an inverse demand function, let's say. It's got two unknowns. That means we can't solve this, because think about it for a moment. What if Q is 1? That's fine. If Q is 1, then P is going to be 120 minus 5, which is 115. That looks like a solution, doesn't it? But what if we say, but no, Q is 2, in which case P is 2 times 5 is 110. Hopefully you can see that. So what are you to do? There's an infinite number of solutions. So the important thing to recognise about that is that we just don't have enough information to solve it. So what do we need? We need another equation that links P and Q. So let's get one. Let's say we've also got P equals 20 plus 5Q. So we have one equation for every every unknown. Two equations, two unknowns. We've got two bits of information about the relationship between P and Q. This we can solve. So how do we do that? Well, these are one of the more simple ones, because look, what do we notice? We notice that P is equal to that, and P is equal to that. So it stands to reason then, doesn't it, that that must be equal to that. It just has to be. So we can straight away write it as a single equation with only one unknown. So now we're back to the kind of algebra we've done before, where we just have to rearrange it and make Q the subject, and we can find the answer. And then once we know Q, P is a simple step away. So what are we going to do there? Well, as we remember before, we want to put all the x's, or in this case, all the q's onto one side. So which side will we pick? We're going to pick this side, because look, this has got positive q's on it, so that's like a base for our q's. This has got negative q's, which is a bit sort of iffy, isn't it? We don't really want those. So let's say this looks like a healthier side to make our q side. So let's get all the q's over to this side. Now, when we first started learning linear algebra, we were doing this thing where we'd say, let's get rid of the q's on this side. How do we get rid of the q's on this side? Well, if we have negative q's on this side, if we add 5q to this side, it neutralizes it, doesn't it? It gets rid of the q. But if we add 5q to one side, we absolutely fundamentally must add it to the other side. So this is how we started taking our painful first steps with linear algebra. So this means 5q plus minus 5q, the q's just disappear. And here we've got 20 plus 5q plus 5q. We still don't know what q is, but we know we've got 5 lots of them, and here's another 5 lots of them. So we've got 10q. Okay, so that's how we started off, but I'm going to sort of standardize on looking at it the other way, which is where we're going to talk about moving things to the other side. Now, we can move any of these terms to the other side. The only price of doing so is to change the sign of it. So we'd like to get this one over to that side, which will give us exactly what we want. And if we move a minus term to the other side, it becomes a positive, which is good. So here's me moving it to the other side. And there's that popping up on the other side, and it's positive. So now we've got 10 lots of q, and we've got some numbers, but we want just q's on this side, because when we get just q's or x's on one side, we're almost there, aren't we? So that means we want to get this one out of the way. And so we're going to move it to the other side. And if we move it to the other side, we have to change the sign. So here we are, 120 minus 20 equals 10q. So that means that 100 equals 10q. So we're almost there. but let's just go through the fundamentals again. So we now know what 10 lots of Q is, but we're not interested in 10 lots of Q, we're interested in just one Q. That's what we want. We want to know the value of Q in this equation. So how do we, if we have 10 Qs and we just want one Q, then what we have to do is divide that by 10. And if I divide this side by 10, I must divide the other side by 10, because whatever you do to one side of the equation, you must do to the other side. So here I am, I'm dividing 10Q by 10, which means I get a single Q. I've got 10 lots of Q, divide that whole thing by 10, I get a single Q. You could think of these as just cancelling out and leaving Q. And 100 divided by 10 is nice and easy, it's 10. So it turns out that Q is 10. So once we know that Q is 10, take another colour, we can take either of those equations, doesn't matter. We know that P equals 20 plus 5Q. So wherever we see a Q, we can now replace with 10. So we've got 20 plus 5 times 10. I'm just substituting in 10 because I know the value of Q. That's 5 equal 20 plus 50, and that's 70. So the answer, the solution to this equation is, and I'm probably off the screen here, is Q equals 10 and P equals 70. So here's another pair of simultaneous equations. So again, we want to find the unique pair of values that solves both of these equations simultaneously. That's why we call them simultaneous equations, because we need them both. We need to solve them at the same time. And there is only one combination of P and Q that solves these, one unique combination. So this one's not quite so easy as before, because remember we had P equals and P equals before, so we could just put the other sides equal to each other. Here we don't have that. If we wanted, we could decide, well, I will set that up. I will make P the equation and P the equation and just set them equal. That's fine, that's an alternative way of doing it. Or we're just going to do, this time we're going to do some substitution. We're going to find a substitution for one of the variables and then put it into the other equation. So here we go. The easiest substitution here would be to say, right, I'm going to work out what P is, which means I'm going to make P the subject, which means I need to move 2Q over to the other side of the equation. And remember, when I move to the other side of the equation, it changes sign. So here it is. So I've moved it, it's become negative. So I now have an expression for P in terms of Q, which I can now substitute into the other equation. And then I won't have any P's, I'll only have Q's to solve. So here's this equation. And wherever I see a P, which is here, I'm going to put in my expression for P. So here we are, we've got one equation with only one unknown. So again, it's a bit of linear algebra to solve it, and then we're done. So let's get rid of this. Oh no, we'll leave it there. So I need to expand these brackets for Q. I've got a 3 outside the brackets, which means I need to multiply everything inside the brackets by 3. Here we go. 3 7s are 21, minus 3, because I've got 3 lots of minus 2Q. So I've got minus 6 lots. Minus 2 lots of Q times 3 is minus 6 lots of Q. Good, so I can collect like terms, which means I can put the Q's together. Oh, and look what I've got. I've got 4Q minus 6Q, so I'm going to have minus 2Q. Plus 21 equals 11. Now, I don't like that minus 2Q, so best practice algebra is to make it positive. So I'm going to put it over to the other side and make it positive, and that will be my Q side. So here we go. 21 equals 11 plus 2Q, so I moved it to the other side, to make it positive, and now I need to move 11 to the other side, so I have to make that negative now. So I've now got 21 minus 11 equals 2Q, that's 10, and if I divide both sides by 2, I will get a single Q. So I see that q equals 5. I might be off the screen there. So here we are, we have q equals 5. That's part of the solution. Take either of those equations and substitute in that value. So here's this equation. Everywhere I see a q, I put in a 5 plus p equals 7. So can you see I've rewritten that and I've substituted in the value of q that I know. So I'll multiply out those brackets. I've got 10 plus p equals 7. I've got to move this to the other side because we want p all on its own. It's going to be 7 minus 10. And here's my other solution. So my pair of solutions is q equals 5, p equals minus 3. So let's look at another one. So number of ways of doing it, but the simplest way to do this is just to use this as a substitution into there. We could do it any other ways. We could make p the subject and substitute it into there, but the quickest route here is just to replace this q with that expression. So let's do that. So we've got 5p plus this whole thing, 2p plus 10 equals 80. So which side are we going to put the p's on? Well, they're pretty well made their case here. It's got to be on this side, isn't it? So we've got 7p plus 10 equals 80. We want p all on its own, so let's get the 10 to the other side. So that means it's going to go negative. 7p equals 80 minus 10, so 7p equals 70. And hopefully you can see that we're going to divide both sides by 7 so that we get a single p here. Because whatever that number multiplied by the p is what we divide by. So we've got 7p divided by 7, which is a single p. And we've got 70 divided by 7, which is 10. So we know one of our unknowns, so now we're going to just substitute in and find q. So let's take another colour. So we could use either of those equations, it really doesn't matter. Let's use this one this time. So we know that, I'm going to do it here, 5p plus q equals 80. We now know that p is 10, so anywhere there's a p we substitute in 10. So this is 50 plus q equals 80. So we just need to get 50 of it over to the other side, which means it goes negative. So q equals 80 minus 50, q equals 30. So here's our unique solution, our new unique pair of p and q. So how about a little Keynesian economics to practice our simultaneous equation skills? So let's look. We've got an expression for national income equals consumption plus investment. We've got a value for investment and we've got an expression for consumption. So can we put it all together and find consumption and income that puts it all into equilibrium? Well, let's look at y. We can substitute in for c and for I in one go. So let's do that. So y will become, wherever we see c, we can substitute in this expression. So that's c, and now I want to add I. We actually know the value of I, so let's put that in. And so now we've got an expression that only includes one unknown, which is y for income. So how can we tidy this up and find a value? But first we might as well put these two together, yeah? We've got 40 plus 20, so let's simplify a little bit. We can say it's 60 plus 0.5y. So we need to get those y's together. Which side is going to be our y side? Well, it's going to be this side because we've got a whole y there. We've only got a half a y here. So we're going to do our thing by moving the half y and it will become negative on the other side. So now we have to work out what y, a whole y, minus a half of a y is. Well, if we take a full something and subtract a half of something from it, we get a half of something remaining. Okay, so it's 1 minus a half lots of y becomes half of y, 0.5y. All right, so we now have this decimal on this side, but we are interested in what a whole y is. So we've got half of y, so hopefully you can see that we're going to multiply both sides by 2. Remember, we can multiply by anything as long as we do it to both sides. So my equation is still balanced. So 2 lots of half y is now a whole y. We could put a 1 in front of it, mathematically correct, but doesn't look very stylish mathematically. It's a whole y equals 120. So we know what national income is. The only thing we don't know now is the equilibrium level of consumption. So we're going to look at C now, and C equals 40 plus a half of y. But we now know that y is 120. So C equals 40 plus half of 120 is 60. So C equals 60. So we now know what income is. We now know what investment is. We know what income is, and we know what consumption is. And here are 4 questions for you to try yourself. So freeze the video, and then I'll show the solutions.